Okay, so here is the official definition of division for rational numbers. So if I want to divide a over b divided by c over d, then it is equal to e over f if and only if e over f is the unique rational number such that c over d times e over f equals a over b. This is the same definition we've been using all semester for division. We define division in terms of multiplication. The only difference here is that now we're dealing with rational numbers. So instead of writing whole numbers or integers, we're writing a rational number. Notice if we're dividing two rational numbers that have the same denominator, then it's sufficient just to divide the numerators. If our denominators are different, we can rewrite with common denominators, and then it's sufficient to divide the numerators. Okay, so here I've got a over b divided by c over d. The common denominator here is bd, so I need to multiply the first fraction on top and bottom by d and the second fraction on top and bottom by b. And now we can use the fact above to say that's just AD divided by BC. All right, now when you're doing this with your students, they eventually recognize that A divided by C over D is equal to A over B times D over C. So we multiply by the reciprocal of the number we're dividing by. Okay. So that's where that comes from. All right, I'm going to skip this example in the video. You already have the answers in your slides, and so if you have questions, please let me know. But let's look at the next problem. I've got 35.5 yards of material available to make towels, and each towel requires 3/8 yards of material. How many towels can I make, and how much material will be left over? Here I want my answer in yards. Okay, so let's start with how many towels. Well, I have 35.5 yards of material, and I want to divide it into towels of length 3/8 yard. So this is a division problem. I want 35.5 divided by 3/8. Now the best way to do this is to write 35.5 as an improper fraction. So 35.5 is going to be 71 over 2, and dividing by 3/8 is the same as multiplying by 8 over 3. So I'm going to have 71 times, well, let's do some cancellation before we do that. So I can cancel a 2 out of the top and bottom, so I'm left with 71 times 4. Whoops, over 3. And let's do some scratch work. 71 times 4 is, I have a 4 and then a 28. So 284 over 3. So I can have 284 over 3 towels. But we really want whole towels, right? So I need to give a whole number, and that means I need to divide, right? So 284 divided by 3. How many times does 3 go into 28? Nine, right? 3 times 9 is 27. And I'm left with 14. How many times does 3 go into 14? 4. I'm going to subtract 12, and I'm left with a remainder of 2. So 284 over 3 is equal to 94 2/3 towels. So how many towels can be made? 94 towels. And how much material will be left over? Well, the 2/3 is my remainder, or my remaining material. But this is in units of towels, right? So I have 2/3 of a towel left. But what is a towel? A towel is 3/8 yards of material. So I have 2/3 of 3/8 yards of tells us multiply. So I have 2/3 times 3/8 yard, which when you multiply, you're going to cancel the 3's. 2 goes into 8 4 times, and I'm left with 1/4 yard left over. Okay? So just be careful of the units on your material. There's a little extra work in part B. All right, how about this one? A bookstore has a shelf that is 37.5 inches long. Each book that is to be placed on the shelf is 1¼ inch thick. How many books can be placed on the shelf? So you want to recognize that this is a division problem, right? I'm thinking about my shelf and I want to divide it into how many books I can put on it. So I want to solve 37.5 divided by 1¼ and make sure that your units are the same. In this case, they are. All right. Again, we should convert to improper fractions first and then do the division. For the sake of time, because I know your attention is limited, I'm going to let you work this one on your own. If you're not sure about your answer, please contact me and we can look at it together. Let's move on to the next example. Whoops, actually I've got the answer here. Nope, I've got the start for you. Okay. All right, so our last topic in this section is exponents. So now I'm thinking of a rational number, a, and I've got integers m and n as my exponents. If I take a to the power m, that means multiply a by itself m times. Same property as we've seen before. When I take the same base and take a to the m times a to the n, I add the exponents. If I take any rational number to the power 0, I get 1. Here's our new property. If I take a to the negative n, that's equal to 1 over a to the positive n. All right, so now I can look at rational expressions. So I've got a to the m over a to the n. That's equal to a to the m minus n. So I've got the same base here, right? The base is a. And so when I'm dividing them, that's the same as taking that base to the difference of their exponents. If I take a to a power raised to a power, that's the same as a to the product of those powers. If I've got a fraction here raised to a power, I can bring the power into the numerator and denominator. That's number 7. Same idea with number 8. If I've got a product of two rational numbers raised to a power, I can rewrite that as each of the rational numbers raised to that power in the product. And this last one, if I take a over b to the negative m, I can take the reciprocal b over a to the positive m. All right, so you should have seen all of these rules in another class at some point in your career. But maybe it's been a while since you've worked with them. I know we worked a little bit with exponents earlier in the semester, but you're going to get some time to work on them again in this section. All right, so let's look at a few examples. So I want to show that the equality or inequality is true in general for rational numbers x, a, and b. So let's start with number 1. I have negative x to the negative 2, and I want to show that's equal to x to the negative 2. Well, my rule says when I take something to a negative exponent, that's the same as 1 over negative x now to the positive 2, which is 1 over Well, it's negative x times negative x. The negatives cancel, so I'm just left with x squared. And now if I work that property backwards, I can rewrite this as x to the negative 2. All right, so that's why number 1 is true. What about number 2? The only difference here is now my exponent is negative 5, and I have an inequality. Well, what happens when I take negative x to the negative 5? That's going to be 1 over negative x to the positive 5. And I'm going to rewrite this as, let's see if I can squeeze this in. Let's think of negative x as negative 1 times x, so that when I have this exponent, I can bring it into each term. So I have negative 1 to the 5th times x to the 5th. But if I take a negative to an odd power, that's going to give me negative quantity x to the 5th. Does everyone see that? Negative 1 to the 5th is just negative 1. And I could rewrite that as negative x to the negative 5th, but that's not the same as just x to the negative 5th. Okay, so that's why that one's not true. All right, what's happening in number 3? Let's start with the left-hand side again. I have a to the negative 4, b to the negative 4, all raised to the negative 2 power. One of my rules on the last slide said that I'm allowed to sort of distribute this exponent in to each term with multiplication. So this becomes a to the negative 4th times negative 2 times b to the negative 4th times negative, moving ahead. Negative 2. And negative 4 times negative 2 is 8. So a to the 8th times b to the 8th. All right, last one. A to the negative 2 plus b to the negative 2 to the negative 1st is not the same as a squared plus b squared. This is the kind of problem where you can see where a student might make this mistake because they're thinking they can do the same move as they did in number 3 to multiply those exponents. But we're not allowed to do that here because we have a sum. Okay, so if I have a to the negative 2 plus b to the negative 2 to the negative 1st, I'm going to work on the inside first. A to the negative 2 I can write as 1 over a squared. And b to the negative 2 is 1 over b squared to the negative 1st. And I'm going to write this as a single fraction. So I'm going to get a common denominator and combine it. For the sake of space and because I'm confident you could do this on your own, I'm just going to show you what we get if we write those with a common denominator. Now what happens when I take that to the negative 1st power? Well, I'm allowed to rewrite it as the reciprocal, a squared b squared over b squared plus a squared, all to the 1st. And that pretty clearly is not equal to a squared plus b squared in general. All right, now what if we put some numbers in here? Okay, so I want to start with 9 to the 4th times 27 to the negative 2nd. I'm going to write 9 and 27 with their prime factorization. So 9 is 3 squared. So I have 3 squared to the 4th times 27 is 3 cubed to the negative 2. So I have 3 to the 2 times 4 times 3 to the 3 times negative 2. I have 3 to the 8th times 3 to the negative 6. And our rule is we can, if we have the same base, which we do, we can add those exponents. So I get 8 plus negative 6 or 8 minus 6 in the exponent. So 3 squared is my answer. How about 20 squared divided by 2 to the 4th? Let's rewrite that as 20. Well, let's factor 20 first. 20 factors as 4 times 5, and 4 is 2 squared. So I have 2 squared times 5, all to the power 2. And I'm going to rewrite the division as a fraction here, divided by 2 to the 4th. I'm allowed to bring this exponent in to each term, right? So I get 2 squared squared times 5 squared over 2 to the 4th. 2 squared squared is 2 to the 4th times 5 squared over 2 to the 4th. And here it straight up cancels, so I'm left with 5 squared. All right, last one. No real numbers here. I'm going to use the same rule to first distribute the negatives in. So I get x cubed to the negative 2 times y to the negative 4th to the negative 2. So I get x to the negative 6 times y to the positive 8. And my answer says express your answer without negative exponents. So what can I do to rewrite x to the negative 6? Well, I can use that rule that says it's 1 over x to the positive 6 times y to the 8th. And we could write that as a single fraction. Y to the 8th over x to the 6th. Okay. All right, so try the last problem in the lecture and then work on the homework. Please let me know if you have any questions.